Hello, geometry students. Today we're going to be working on the Unit 6 activity. It has to do with density and three-dimensional objects. So we're going to be working on that today. If you still need help afterwards, after you've looked through the lesson and tried to figure it out, you could always email me. My email is ttrigg@ofy.org. Okay. Well, without further ado, let's go ahead and get started on geometry unit 6 activity. Okay. So I'm going to share my screen with you guys. Okay, cool. So your unit activity should look something like this. Okay. I go to page 5 here, 5 of 9, and it should say finding density. Okay. Go ahead and follow along as I read out loud. All objects have mass. Mass is the amount of material in an object, usually measured by its weight. Earlier in this unit, you studied the volume of objects. When you combine these two concepts, you get a useful measurement called density. Density of an object is its mass per unit of volume. Imagine two objects in which the larger one actually weighs less than the smaller one. The difference in weight is attributed to density. Okay, so like they're talking about, imagine you had like maybe a bowling ball, maybe that's too big, maybe like a steel ball, okay, small steel ball that you can hold in your hand, okay, versus like a big thing of styrofoam, okay. The steel ball would weigh more even though it has less volume. So therefore, we'd say that the steel ball has more density. Okay, continuing on. Consider a candle that has a volume of 96 cubic inches and a weight of 44.16 ounces. What is the density of this candle? The density is defined as its mass per unit volume. So simply divide the mass of the candle by its volume. So to get the density, you take the mass, 44.16 ounces, divided by the volume, 96 cubic inches. And so you get 0.46 ounces per cubic inch. That would be the density. In this case, you are finding the average density of the candle. In most cases, you will be finding the average density of objects because most objects do not have a uniform density. For instance, the portion of the candle where the wick is might have a different density than the rest of the candle. Now that you know about density, let's work on some applications. Harold is a woodworker and is interested in finding the density of two different types of wood. He bought a pine log that has a 5-inch radius and is 30 inches long. The weight of the log is approximately 42.63 pounds. He also has an oak board that is 5.5 inches wide, 1.5 inches thick, and 3 feet long. The board weighs approximately 8.05 pounds. Okay, which shapes can you use to model the log and the board? All right, so I'm going to pull up a Jamboard real quick. And that way we can look at what we're talking about. So a log, you know what a log looks like this. Okay, so what kind of shape is that in general? Well, we would say that that's a cylinder. That's a cylinder. So a log is a cylinder. And the board maybe looks like this. Okay. And so the board would be a rectangular prism. Right, so that's what you'd put for these ones. So for the log is cylinder. Cylinder. And for the board, it's a rectangular prism. Okay. What is the density of the pine log? So to find the density, we have the formula before. The density is and let's go back and look, you could see density is the mass divided by volume. Okay, so we want the mass of the object divided by the volume of the object. So the mass divided by volume. I want you to think of mass as weight. Now, mass and weight aren't exactly the same thing, but that's basically how we're measuring it in this case. All right, so in this case, for the log, according to the problem, has 5-inch radius, 30 inches long, and has a weight of 42.63 pounds. 42.63. So for the log, its mass, we're going to say 42.63, and that's in pounds. Okay, so that's the mass. So we're going to find the density. We do the mass divided by the volume. All right, now how do we find the volume of a cylinder? Well, for the volume of a cylinder, what it is the area of the circle times the length here. So it's the area of like one of the bases times the length of this. So the area of the circle, formula for the area of a circle is pi r squared. So it's going to be pi times the radius squared. That would be the area of the circle. Then times the height, or in other words, the distance between the two bases. Okay, well, they give us that information in the problem. So it says the log has a 5-inch radius and 30 inches long. So r, the radius, is 5 inches, and the height, or the length between here, is 30 inches. So our volume for the log will be pi times 5 squared, because 5 is the radius, times 30. Okay. Now for pi, you could just go ahead and use 3.14, and that's fine. So we're going to have 3.14. If you want to be more precise than that, you could use 3.14159, but I'm fine with you using 3.14. 5 squared is 25. So we're going to multiply that. And then times another 30. So go ahead and multiply that on your calculator. If you need a calculator, you can find one through Googling it. The Desmos scientific calculator is very good. So that's the one I would suggest. You could Google that. Desmos scientific calculator. There's also, they have a really good graphing calculator as well, Desmos graphing calculator. So if you need a calculator, I'd go with that. But anyway, when you multiply this, this gives you the volume of the log. So in our case, that's 2355. And that's our volume. And this is in inches cubed. Okay. So 2355. So to figure out the density, you just divide that. So we have 42.63 divided by 2355. And we get 0 or 0.018. And this is pounds per cubic inch. Okay, so that's the density of the log. All right. So this is again the density for the log. Now we need to find the density of the board. The density of the board. So we need to go look at that information for the board. So for the density, it's generally the same formula. It's the mass divided by volume. And in our case, it says, as far as its mass, it's 8.05 pounds. Okay. And its volume, to find the volume of a rectangular prism, like this board, you would do length times width times depth, or length times width times height. You may have seen it as well. Okay. Now in our case, it says 5.5 inches wide, 1.5 inches thick, and 3 feet long. So we're going to have 5.5. You're just going to multiply these three dimensions together. So 5.5 times 1.5. And then it says times, and it's 3 feet long. We want those in inches because these are both in inches. We want everything to be in inches. So 3 feet long. 3 feet, how many inches is that? Well, there's 12 inches in a foot. So 3 feet would be 3 times 12. That's 36. So 3 feet, we're changing that to inches, 36 inches. Okay, multiply those together to find the volume of the board. 5.5 times 1.5 times 36. 297. Hopefully you got the same thing. Go ahead and divide those numbers. The 8.05 divided by 297, and that'll give you the density of the board. The density of the board is a little bit more than for the log. We got 0.027. And again, that's pounds per cubic inch. All right. So you can see the density of the log is different than density of the board. In other words, if you took the same amount of the log and the same amount of the board, like a handful of it, same amount though, the log would weigh less than the board. And you could kind of see that because they're made out of two different woods, right? It says the log was made out of, does it say? Yeah, pine. The log was made out of pine and the board was made out of oak. So you can see in this case, at least in this example, the oak is more dense. Okay, so I want you to go ahead and show that work here, okay? So all the work that we put here, I want you to put it, okay? Put this onto here. So you could use the equation editor. So you might be like, oh, the density of the log, and then you'd show the work, okay? So you'd show the work that all this work for the log, okay? And you'd use the equation editor. So you'd use this equation editor and put in all the work right here. So you might have D equals, and you would have a fraction. We have M for mass over V for volume. And you'd put down at least a little bit of the information. The more work you show, the better grade you're going to get. So just make sure that you show your work, show the information, and answer the question. Okay. If you slack and don't show good work, then you're just not going to get full credit. Part C, what is the density of the oak board? Oh, wait. We did both these already. So the density for the log goes here, density for the board goes there. Okay, cool. If you had a block of each type of wood of the same dimensions, how would their weights compare? So I kind of already explained this earlier, but as a refresher, if you had the same amount of each of these materials, the oak would weigh more because the oak board had a higher density than the pine. So I want you to explain that there, that because the oak had a higher density, if you took the same amount from the oak and the pine, the oak one would weigh more because it has more density. Okay? So you can briefly explain that there in your own words, please. Part E, water has a density of about 0.036 pounds per cubic inch. You might know that wood floats on water. What can you conclude about the densities of objects that float and the densities of objects that do not? Review your results from part B and C before deciding. Okay, so basically here's what you'd want to explain here, that any object that that floats in water, it floats because it has less density than the water. So any object that is less dense than water will float. Any object that is more dense than water will sink. So something like styrofoam, it's less dense than water, so styrofoam floats. Whereas something like a rock is more dense than water, so it sinks. In this case, would our two pieces of wood, the log and the board, would they float or would they sink? So in other words, are they more dense than water and hence will sink? Or are they less dense than water and would float? So I want you to go ahead and figure out the answer for that, okay? All right, we're moving on. Okay, again, if you need to pause at any time, pause the video, rewind it if you need to hear something again. So yeah, you have that. Okay, the story of Archimedes. Please read along as I read aloud. About 2,200 years ago, one of the most famous mathematicians in history made a major discovery. The mathematician was Archimedes, who was presented with a problem by King Huron II of Syracuse in Sicily. The king had given a bar of gold to a jeweler and ordered him to make it into a crown. After receiving the crown, the king suspected that the jeweler had replaced some of the gold with an equal weight of a cheaper metal, like silver, and kept the remainder of the gold for himself. The king had no way to determine whether this was true. So he gave the crown to Archimedes and asked him to devise a way to find out. Okay, stop right there. So the king gives a piece of gold to the jeweler makes a crown. Okay, now the king's thinking, oh wait, the king's thinking, did the jeweler really use all the gold for my crown? Or did he take some of the gold out and put it as silver? The jeweler would probably make sure that they weighed the same as the original gold, but could have taken some of the gold out on his own for himself. Okay, reading along. At the time, Archimedes knew that gold was more dense than silver. So if the volume of the crown was greater than the volume of the bar of gold, they would have proof that the jeweler had stolen some of the gold. However, Archimedes had no way to find the volume of an irregular shape like a crown. So back in Archimedes' day, the only thing we knew how to find volumes for were things that were normal shaped, like a cylinder or a rectangular prism, because we had formulas for those. So Archimedes had formulas. He could find regular shapes volume, but not irregular shapes like a crown. Okay, Archimedes struggled with this problem for a long time. One day, he went to take a bath. As he lowered himself into the bath, he noticed that the water rose. As he continued to lower himself into the water level continued to rise. He was so excited at his discovery that he jumped out of the bath, and before he could remember to put his pants on, went running through the streets yelling, "Eureka, Eureka," which in Greek means, "I found it, I found it." He now had a way to measure the volume of the irregularly shaped crown. In Archimedes' case, the jeweler had indeed stolen gold from the king. This did not end well for the jeweler, as you can imagine. Okay, so what did Archimedes discover? So part A, it says, a key component to the story is that the jeweler deceptively replaced an equal weight or equal mass of gold with silver. How does this action result in increasing the volume of the crown? Explain using one or more equations. So basically, we just want to explain that since silver is less dense than gold, silver is less dense than gold. Gold. Silver is less dense than gold. A crown made out of silver would have greater weight, greater volume if it had the same weight of a made of silver would have greater volume if it had the same weight of a crown made out of gold. So if I had 2 crowns, so if I had a pound of silver to make a crown and a pound of gold to make a crown, I would have more silver because silver is less dense. Okay. Yes. Okay. What did Archimedes discover in the bath? Why was he so excited? Describe the discovery using geometric terms. What do you predict Archimedes did next with his new discoveries? Well, so when Archimedes got into the bath, the water rose, right? And which we've probably all experienced this, that when we put something in water, the water level rises. That allows us to find the volume of any object. Any object that we can put in water, we could just look at the way the water rises and be able to calculate how much the water rose, and therefore we'll be able to calculate what's the volume of the object we put in there. So however much the water rises, that tells us the volume of the object. So therefore, we can find now, since Archimedes discovered that, we have since been able to find the volume of any object we want to find. Any object, a crown or anything. If you wish to find its volume, you simply dunk it in water and measure the amount that the water rises. Okay, so I want you to explain that there. Okay, that Archimedes was able to find the volume of objects by measuring the amount of water displacement. When the object is submerged. Okay, I apologize if I spelled some things wrong. That's okay. Anyway, and then I want you to also explain what do you predict that Archimedes did next with his discovery? Okay. Remember, he was hired by the king to make this discovery. So what do you think Archimedes did next? Okay, next page, page 7. And you can go ahead and pause and answer that question. Displacement and buoyancy. Buoyancy is the ability to float in a liquid such as water. Archimedes' experience with water displacement in the bath gave rise to Archimedes' Principle, which states that the upward buoyant force or push exerted on a body immersed in a fluid is equal to the weight of the fluid the body displaces. In technical terms, buoyancy is the upward force exerted by a fluid on a body when the body is immersed in the fluid. Okay, that was a lot of big words and interestingly phrased sentences. But basically, here's the idea. When you put anything in water, there's a force pushing up. And if the force pushing up, by the way, the force pushing up is the buoyant force. That force pushing up, if the buoyant force is greater than the amount of force caused by the weight of the object, then that object would float. Okay. This also explains why helium balloons float in air, because their density is less than the density of the air around them. So the displaced air pushes up for a buoyant force, which is less than the weight of the helium. Okay, that's also why boats float, because the buoyant force pushing up is greater than the amount of weight pushing down on the ship. Okay. Now, how much buoyant force do you get depends on the object. So let me draw a picture here. So let's say I have a boat. Here's my boat. And it's partially in the water. So here's my water. Okay. So how much water has this boat pushed out of the way, right? The boat had to push some of the water out of the way to be in the water. Well, it pushed away this much water. Okay. So if you imagine that that you could see and measure and see and weigh all the water that this boat displaces, you would be able to figure out how much weight of water it displaces. Okay, so let's say it displaces 1,000 pounds of water. So the amount of water that this is displacing is 1,000 pounds of it. Well, then that means there would be an upward force of 1,000 pounds, the buoyant force. Okay, 1,000 pounds of force pushing up. Well, what would that mean? That means that if you put in more weight in here, if you put additional weight into the boat, if you put in more than 1,000 pounds, it would make the boat go lower. Okay, so if you put in, for example, 900 pounds, the boat wouldn't change. But if you put in, let's say, 2,000 pounds, the boat would be pushed down more until it reached equilibrium, until there was 2,000 pounds of water displaced, and then it would be steady again. Okay, so it would go down. If you put in more than that, it would still sink down more. Okay, hope that kind of makes sense of what they're trying to say. But that's Archimedes' principle. So however much water is displaced, the weight of that water gives you a buoyant force pushing up. Making use of Archimedes' principle, displacements, and buoyancy explain why some objects float on water, but others do not. Use the diagram to help you decide. Help you decide what? So I want you to just explain kind of what I was just saying, that if the density of an object is less than the density of water, then it will float in water. Okay? I want you to just say that there, okay? If the density of an object is less than the density of water, then the object will float in water. Okay, I hope that at least kind of makes sense. This goes for any fluid, right? Like will an object float in what's another type of liquid or fluid? I guess maybe liquid metal. You would find the density of that liquid metal, and you'd find the density of an object, and you could figure out if the object would sink or float in the liquid metal. If it's less dense than the liquid metal, then it would float. Okay. The Titanic is one of the most famous passenger ships in history. Search the internet to determine how much the Titanic weighed in metric tons. Okay. I went ahead and did that for you. 46,000 metric tons. Easy peasy. The hull of the ship should be the only portion of the ship that is below the water. Therefore, at a minimum, how many tons of seawater should the hull of the Titanic displace while it's in water? So think about that. If the Titanic weighs 46,000 metric tons, how much water must the Titanic displace? What's the weight of the water that the Titanic must displace in order to float? We talked about that here. So if you're stuck, go ahead and rewind and watch this part again. Okay? If you're still stuck, you could always email me. Okay, I want you to try to figure that out on your own. Okay, part D. Search the internet to find the density of surface seawater in kilograms per cubic meter. I already did that for you, and it's 1,027 kilograms per 1,027 kilograms per cubic meter. Convert the density of surface seawater to metric tons per cubic meter. All right, so we need to convert from kilograms to metric tons. Metric tons. So we're gonna Google that. Kilograms to metric tons. Okay. 1 kilogram is 0.001 metric tons. Well, for the water, it was 1,027 kilograms, which is 1.027 metric tons. Okay. So what we would do is we would take the weight, 1027, and we multiply by the conversion, which in our case was 0.001. Okay. So that means 1,027 kilograms will equal would equal 1.027. Easy peasy. Based on your calculations so far, how many cubic meters of water did the hull of the Titanic have to displace to stay afloat? Okay, so if you recall, the weight of the Titanic was 46,000 metric tons. And each cubic meter of water was 1.027 metric tons. So if you divide that, that'll tell you the amount of water that must be displaced in order to keep the Titanic afloat. Okay, and it'll be in meters cubed. So whatever answer you get here, it'll be in meters cubed. Okay, so I want you to divide that, and we get 4600. Or was it 46,000? Is there another zero here? I think so. Divided by 1.027. Let me just make sure that that's correct. Yeah, 46,000. Divide that, and we get 44791 cubic meters. All right, so I want you to go ahead and put this work in for this problem. And run next. Last page. It's not even that long. Density and population. The concentration of people or other species in a given area is called population density. When dealing with population density, we use area instead of volume because it is a better measure of living space. Find the population density of a city by dividing its population by its square miles. Okay, part A. Use the internet to find population of Ohio. Use this site to estimate the area of Ohio in square miles. All right, so first let's go to this site. I already have it loaded right here. Okay, it should look something like this. If you try to scroll in or out, it'll just zoom in, zoom out. So if you want to scroll up the page or down the page, you need to use the scroll bar on the right or the arrows. Okay. So here's how this website works. Kind of took me a while to figure out, but let's go ahead and we want to look at Ohio, which is right here. You can see where Columbus and Cincinnati and Cleveland are. And I'm scrolled in about right here. Okay. So I can still see all of Ohio. If I scroll in any more, I could scroll in a little bit more here. Here we go. So here's Ohio. If I scroll in any more, I can't see the whole thing. So I don't know if I want that. I want to be able to see the whole thing. Okay, so I got Ohio here. Okay, cool. Now, over here on the right, you can see this. I'm on World Topo, and I think that one shows up better. If you just use regular map, it's hard to see what's going on. Okay, so you could switch it to terrain. That looks all right. But I think World Topo, you could see the border of Ohio pretty good there. Maybe US Topo, how does that look? Oh, it won't let me. So World Topo, I think that's probably the best bet here. Okay, so now you want to go to boundaries, so click boundaries. And then you should be able to click, and I want to try to click around the boundary of Ohio. Okay. Just kind of click all the way around. Okay. Goes here, and here, and here, and here. So just click all the way around the shape. Make sure I don't want a piece of West Virginia here. Click here. Cut across there, here, here, here. Okay, I think that looks pretty good. All right, so now you can, if you use the scroll bar on the right and you lower down, you could see the different pieces of information here. So it gives you the perimeter and the metric and area. You could see for area, it's 1.008 times 10 to the 11 meters squared. In miles, that's 3.892 times 10 to the power of 4 miles squared. Okay, or in other words, 38,920 miles squared. Okay, that's the estimate I got. So for the area, my estimate was, I forgot what it was, 38920. 38920 miles squared. Okay. Yours might be a little bit different. That's fine. Yours might be quite a bit different. That's fine. Okay, not a big deal. We also want the population of Ohio. So that's just a little Google search here. Population. Oh, I've already searched it before, as you can see. 11.69 million. 11.69 million. So population. 11.69 million. So that's 11. 690,000. Throw some commas so it's a little bit easier to read. I think that's what the number was. Yeah. Okay, cool. All right, so we want to now find the population density. Okay, so for the density formula, we use the equation editor here. What you do is you divide the area divided by, I think I made a mistake. This shouldn't be area, it should be population on top. Population divided by area. So in our case, our population is 11690,000 divided by 38920. And that will equal, with our calculator. Now you might get a slightly different number for area. That's fine. Okay, don't worry about that. Okay, it's going to be slightly different for each person. So yours should be slightly different. That's okay. So I've got about, for me, I got about 300 people per square mile. People per square mile. Mile. Okay. All right. Oh, look how nice that looks. Okay. Yeah, so show your work. Show your work. Moving on, part B. Let's see what they got. They got 285.5. It's pretty close. Okay. Use the internet to find the actual area of Ohio. So we have the population of Ohio already. Let's find the area of Ohio. 44,825. 44,825. Which means my estimate's very bad. That's okay though. All right. So now we want to find the population density. Okay. So again, the population. Let's do the area first. So the area is 44,000. What was it again? 44,825. Okay. Square miles. Population. That didn't change. So that's 11.69 million. So 11,690,000. Okay, cool. Now, I want you to go ahead and find the population density. Okay. It's the same as what we did for the population density here. You take the population divided by the area and to get the population density. Okay. So go ahead and do that and then compare how it's different to your estimate here. So is your estimate higher or is your estimate lower? Okay. So again, find the population density for using this data, just like how we did here, and then compare it to the answer you got in part A. Okay. Part C. How do you think the population density of Cleveland, a major city in Ohio, compares to the population density of the state? Explain your answer. So, in big cities, is that going to be a higher population density or a lower population density? What do you think? So a big city like Cleveland, do you think there's more people packed in there and hence a higher population density, or fewer people and a lower population density? Okay, I want you to think about that and go ahead and answer this question. Think about big cities you've been in, okay? If you're still not sure, you could always email me. All right, well, that's it for this activity. I hope that all made sense. Hope that all made sense. I hope you guys get it. If you're still struggling, email me. Okay, you always have that option. You could always, if you just need me to walk you through every bit, that's fine. Email me. Again, my email is ttrigg@ofy.org. Okay? So this is the end of the activity explanation. So, and I will see you guys next time with the Unit 7 activity. Okay? Take care.